Good afternoon, everyone. I'm Norman Wahlberger, and we're here at the University of New South Wales in this course on the history of mathematics. And we're in lecture 15 today, Complex Numbers and Algebra. We're following John Stilwell's book, Mathematics and Its History. I think we're in chapter 14 of that book. So we're going to talk about complex numbers today, a rather interesting subject that got going in the 1600s, slowly, 1700s, speeded up. So these days, complex numbers are, of course, routinely discussed in high school. We learn that a complex number is something of the form a plus bi, where I could also possibly be written as the square root of minus 1 because it's defined by the property that its square is minus 1. And the a's and b's are so-called real numbers. And students learn that they can graph these complex numbers in a two-dimensional plane, say with coordinates x and y, and say 1 in that direction and I in that direction there, so that the point A plus BI is represented there, x coordinate A and y coordinate BI. Okay, but this understanding of things took a long time to appear, and mathematicians only slowly and reluctantly started using this square root of minus I, not surprisingly. So I suppose we should start with Stevin, who around 1600 introduced the essentially modern concept of a real number. So he introduced infinite decimals, which then subsequently were called real numbers. And I think that notation goes back to Descartes. Infinite decimal numbers in the usual way, so something like pi is 3.14159, etc., and it goes on in some fashion. And so this extended the Hindu Arabic framework by allowing decimals that go on forever, supposedly, and people were pretty comfortable that this sort of provided a reasonable model for the line. So, for example, pi was somewhere in there, and this was thought of as the real line. Of course, negative numbers took a while for people to acknowledge that negative numbers had the same kind of role, or sort of symmetrical role, as did positive numbers. And it was not surprising that something whose square is minus 1 took a lot longer to work out. These days, students are introduced to complex numbers, or the imaginary numbers, by the quadratic formula. Of course, which goes back much earlier. And of course, when this b squared minus 4ac, the discriminant of the equation, is negative, then what's inside here is something like a square root of minus 1. So for example, if you have an equation like x squared plus 1 equals 0, for example, then, or a more general quadratic equation, in the quadratic formula gives you something that suggests that there should be a square root of a negative number. But generally, people didn't have a reason for considering such solutions. So historically, a quadratic equation, if it didn't have solutions, well, it didn't have solutions. You didn't look for solutions that were outside the realm of investigation. So this is actually not really the historical motivation for introducing imaginary numbers, as Stilwell interestingly points out. One might think that this is where the imaginary numbers first appear in the quadratic formula, which is very simple. But in fact, it's rather the cubic formula, which is much more complicated, that the role of the imaginary numbers was clearer. So let me remind you that for a cubic equation, and we're talking about the work of Del Ferro, Tartaglia, and Cardano here. That if we have, say, a simplified cubic, y cubed equals py plus q, then around 1540 or so, they came up with the formula that y is cubed root of q over 2 plus square root of q over 2 squared minus p over 3 cubed plus the cubed root of the same kind of thing with a minus sign here. Okay, the famous formula of Tartaglia or Del Ferro and Cardano. Now, we see that in this story, there's a square root inside a cubed root, and the square root inside it can give us imaginary or complex values if q over 2 squared minus p over 3 cubed is less than 1, then we're going to get some complex numbers involved here. And an example of that was illustrated by the following example. Suppose we look at the equation x cubed equals 15x plus 4. So if you plug the various values in there, you can check that the formula gives you the solution. X equals the cubed root of 2 plus 11 times the square root of minus 1 plus the cubed root of 2 minus 11 times the square root of minus 1. And this was a little bit surprising because people could see directly that this cubic had actually a real root that was quite obvious. There's this obvious solution, x equals 4. So every cubic has at least one real solution because the graph of a cubic typically looks like this. And there's always at least one place where it crosses the x-axis. But in this case, this formula, instead of giving us x equals 4, it's giving us these cubed roots of these complex numbers involving these mysterious square root of minus 1s. And it was a mystery of how to interpret this. But then a fellow called Bombelli came along, and in 1572 gave the following analysis. He said, well, let's just work with these square root of minus 1s as if it sort of worked. And let's look at, well, I'm going to use Gauss's notation, I, instead of square root of minus 1 because it's a little bit easier to write. So using that notation, if you take 2 plus I and you cube it, then you get 2 plus 11i. So if you use the binomial theorem on 2 plus I, and just use the fact that I squared equals minus 1, collect terms, you get 2 plus 11i. And if you look at 2 minus 1 cubed, then again you get 2 minus 11i. So he saw that you could interpret this cubed root of a complex number within the complex number framework. So that this formula then, using this insight, the cubed root of this should be 2 plus I, and the cubed root of this one should be 2 minus I. And when we add those up, we do in fact get 4. So Bombelli was pointing out that there's a consistent kind of arithmetic underlying this strange square root of minus 1. that actually allows us to solve the cubic. All right, so in the next 100 years, 200 years, people started experimenting with I, especially, using it in formulas to derive things or to shed some light on things, even though they weren't quite confident about what this I really was. So I was sort of sometimes called an imaginary number. And in fact, the early usage was that anything of the form a plus bi was called an imaginary number. The term complex number only came around later. So here are some examples of how I appears. One is the work of one of the Bernoulli brothers, Johann, who in 1712 realized that you could factor, first of all, 1 plus z squared. 1 plus z squared could be factored as 1 plus iz times 1 minus iz. It was a factoring that was possible using imaginary numbers that wasn't possible with real numbers. And so then you could use that to write a partial fraction decomposition of this, to write it as 1/2 over 1 plus iz plus 1/2 over 1 minus iz. Now during this period, most applications involved calculus one way or the other. People were interested in developing the calculus and solving calculus type problems. So Bernoulli was interested in this because if we integrate 1 plus z squared dz, well, that's arctan of z, as Bernoulli realized. Then, according to this formula, the integrals of something like 1 over 1 plus iz, that was some kind of logarithm involving a imaginary number. So this tan inverse function, the arctan function, Bernoulli realized this is somehow connected with some imaginary logarithms. Through this formula. And in a related analysis, he had a look at the following question about what is the relationship between tan of n theta, let's call that y, and tan theta, let's call it x. So how do you write a formula for tan n theta in terms of tan theta? So a version of this that's probably familiar to you. So for example, tan of 2 theta equals 2 tan theta over 1 minus tan squared theta. So that's the case when n equals 2. So we're saying that in that case y equals 2x over 1 minus x squared in terms of y and x when n is 2. And Bernoulli was interested in, well, what happens if we look for higher values, not just n equals 2? What about n equals 3 or 4 or more generally? Okay, so what did he do? So he looked at tan n theta equals y and tan theta equals x. He said, all right, so n theta is going to be tan inverse of y, and theta is going to be tan inverse of x. Now the integral of 1 over 1 plus z squared is tan inverse of z. So that means the derivative of this is 1 over 1 plus z squared. But at that time, people thought rather of differentials rather than derivatives. So they took differentials. These days we would say taking derivatives, but taking differentials, in this expression we get dy over 1 plus y squared equals n times dx over 1 plus x squared. Sort of removing the theta and taking differentials. Well, then with this kind of analysis on these denominators here, we get that 1 over y plus I minus 1 over y minus I dy equals n times 1 over x plus I minus 1 over x minus I dx. And then integrating, we get log of y plus 1, log of y plus I rather, minus log of y minus I equals n times, let's say n times log of x plus I minus n times log of x minus I. And that is, using properties of the logarithm, that log of y plus I over y minus I equals log of x plus I over x minus I to the n. And if the two logs are equal, well then what's inside are equal. So y plus I over y minus I equals x plus I over x minus I to the n. So that was Bernoulli's derivation. He didn't perhaps put in a constant of integration. Usually when we integrate, we have to introduce a constant of integration. So if we put a constant of integration into the formula, then we get another constant here. That's a constant of integration. And then one can show that that's got to always be either 1 or minus 1. So there's sort of two kind of formulas depending on parities. And using that, that's now a relationship between y and x. You can now solve this for y in terms of x. When you do, looks like you're going to have i's involved, but it sort of turns out that when you do the arithmetic, all the i's cancel, and you get a real expression involving expressing y in terms of x. So we can solve y for x. And the answer that we get is quite pleasant. So what do we get when we solve that? Well, I'll show you what it is for n equals 4, for example, and I think you'll get the picture. So when n is equal to 4, the relation is that y, which is tan of 4 theta, equals x to the 4th, 4x, minus 6x squared, minus 4x cubed, plus 1. And I've written it that way so that you can see that it's the coefficients of x plus 1 to the 4th, or all the terms, maybe I should say, the coefficients of x plus 1 to the 4th, but sort of interspersed here, then here, then here, then here, then here, alternating up and down, with minus signs going across. So every term alternates plus minus. So up and down, with plus and minus signs. So x here, x is tan of theta. So if we go back to the n equals 2 case, that was y equals x squared over 2x minus 1. That's the same kind of story. It's really x plus 1 all squared, x squared 2x 1 appearing in the bottom and then the top, bottom, top, bottom, top. We said that one of the main concerns of this time was integration, and a very important problem was how to integrate a rational function. In other words, how do you integrate a polynomial divided by another polynomial? That's a very foundational problem in calculus. And the 18th century mathematicians realized that one approach to this was to try to factor the denominator. So if you could factor the denominator, then you could rewrite this rational function in terms of partial fractions. Okay. So the key is to factor the denominator and then rewrite using partial fractions. So that's still a popular technique that students learn in calculus courses these days. So the key point is that you've got to try to be able to factor a polynomial in order to integrate it. And so the question arises, how can you factor polynomials? So this question led to another question, how to factor polynomials. Could polynomials always be factored? And if so, how? Well, in the 19th century, people started realizing that there was an important theorem floating around having to do with factoring of polynomials. And that theorem became an absolutely fundamental theorem in mathematics, and one that's rather difficult and tricky. So it's the fundamental theorem of algebra. Okay. And it's a result that came into focus in the mid of the 18th century. And the statement of the theorem back then was that any polynomial with real coefficients can be factored into real, linear, and quadratic factors. So the fundamental theorem in the 18th century did not actually explicitly involve complex numbers. This was the original form of it. And it wasn't at all so clear that this was true. And in fact, it's a very subtle business. And a lot of, as we'll see, a lot of very powerful mathematicians had a go at trying to understand this with perhaps mixed results. So one of the Bernoullis, Nicholas Bernoulli, suspected that this might not be true, and he wrote to Euler saying that he thought he had an example of a polynomial that couldn't be factored. It was a quartic polynomial, x to the fourth minus 4x cubed plus 2x squared plus 4x plus 4. So it's one thing to say, okay, well that's factors into quadratic factors. But how exactly do you write it as a product of two quadratic factors? Bernoulli doubted it was possible, and Euler was able to show that he was wrong. There are two factors. The factors are, first one is the quadratic x squared minus 2 plus square root 4 plus 2 square root of 7x plus 1 plus square root of 4 plus 2 root 7 plus root 7. And the other factor is a lot like that, x squared minus 2 minus square root 4 plus 2 root 7x plus 1 minus square root of 4 plus 2 root 7 plus root 7. So the difference is the plus going to minus there and there. So here are two quadratics, and if you have nothing else to do tonight, you can check that Euler was right by multiplying this one with this one, and hopefully all the complexity will disappear and you'll just be left with that relatively simple quartic polynomial. So Euler thought about this. So Euler was one of the people who believed this theorem and was interested in trying to prove it. But Euler was very practical and calculationally oriented, so he first tackled the quartic problem. How do you prove it just for quartic polynomials? How do you prove that if you give it any quartic polynomial, you can factor it into linear and quadratic factors? So Euler gave a proof, but the proof was maybe not quite correct, had some gaps. So Euler gave a proof, not quite correct, for the quartic case. But this showed that this is computationally a difficult problem. And even today, it's still a computationally difficult problem. So there were general proofs that were given shortly afterwards by D'Alembert and by Gauss. But to introduce those proofs, we have to expand the theorem, and we have to go to the complex domain. So we have to look at it from the point of view of a complex valued polynomial. And sort of as a preliminary to that, we have to think about the geometrical representation of complex numbers. It was clear from the work of quite a few people that there was something two-dimensional about complex numbers. For example, Coates, De Moivre, and Euler all studied the equation x to the n minus 1 equals 0. And they realized that you could write down solutions using complex numbers, namely cosine of 2k pi over n plus I sine 2k pi on n. K going from, say, 0 up to n minus 1. So this is around the 1750s. And they all realized that you could interpret these solutions geometrically. So these solutions can be interpreted geometrically by putting everything on a two-dimensional plane and looking at a circle and then putting the points, maybe in some equally spaced, let's say this might be n equals 5, some equally spaced way around the circle forming a regular polygon. So we have a regular n-gon in the unit circle. In a plane where one axis is labeled by 1 and the other axis is labeled by I. Because we're just getting cosine and sine, but we have to interpret that I as a vertical direction in a different direction from the real number line. So here's the ordinary real line, and here's some new imaginary line. So in 1797, there was a Norwegian surveyor, Caspar Wessel, who wrote a paper which was basically ignored by everybody, but it's a very good paper, in which he laid out a geometrical formulation for complex numbers. And he had a vector orientation, perhaps because he was a surveyor. So he said, all right, we'll make axes 1 and I, and we'll think of the complex number a plus bi as a vector. The vector with component a in that direction and the component b in that direction. And then if you have two such complex numbers, say z1 and z2, then he showed that the addition of vectors could be thought of geometrically just by adding the two vectors. So if you add the two vectors, there's z1 plus z2. And more interestingly, perhaps, the product of the two complex numbers is formed by taking these two angles, let's say theta 1 and theta 2, and adding them. So this angle here is theta 1 plus theta 2, the sum of the angles made with the x-axis by z1 and z2. And moreover, the length of that vector, well, its length was the product of the lengths of the original vectors. So to multiply complex numbers, you had to add angles and you had to multiply lengths. And he did that all geometrically. Of course, that's very familiar to undergraduates these days. But as I say, it was sort of ignored. People didn't know about it until about 100 years later, I suppose. There was also another little-known mathematician named Argand, who also around this time gave a geometrical interpretation of the complex numbers operationally. An operational view of complex numbers, say C for complex numbers. And maybe we could state that this way. So if here's our standard real line, then one way of thinking about ordinary numbers is to think of them in terms of translations of this line. That's very familiar. A somewhat less familiar way of thinking about ordinary numbers is to think of them as dilations of the line. So if you think of number 2 as sort of being represented by dilation by a factor 2, or minus 1 being dilation by a factor of minus 1, then Argand said, okay, well, how can we find a square root of minus 1? A square root of minus 1, which should be a transformation, so that when we do it twice, we get a dilation of minus 1. So a dilation of minus 1 is just a reflection in the origin. And he realized that by thinking two-dimensionally, on just the one dimension, it's hard to find a square root of the reflection. But in 2 dimensions, it's possible to find the square root of the reflection. The square root is a quarter turn. So the square root of minus 1 could be represented by a quarter turn. So turn by 90 degrees. So this transformation could be thought of as the complex number I. So we could think of I as being the point that you get at by starting with 1 and applying the transformation, or we might even think about the transformation as being the complex number itself. That way, the product of complex numbers was just compositions of these transformations. So he adopted the point of view that we have today, that you can end up representing a complex number by actually a point rather than a vector. And that was the point of view that Gauss took. So Gauss, Carl Friedrich, the towering mathematician of the 19th century. So 1777 to 1855. He adopted this kind of point of view. He gave the name complex number instead of imaginary number. And he used I. And he investigated complex numbers on and off in his life quite a lot. And in particular, he discovered what was later to become Cauchy's theorem, and he stated Cauchy's theorem, which in Gauss's language was this, that if you had two paths, gamma 1 and gamma 2, and you had some function, say phi of z, then the integral around gamma 1 of phi of z dz was equal to the integral around gamma 2 of phi of z dz, provided that the function phi of z was actually single valued. That meant it was a proper function, and did not take on the value infinity within that domain. In other words, that's Gauss's way of saying that it doesn't blow up, it doesn't have a singularity. These days we would say it's analytic. So this is basically Cauchy's theorem, which he stated but did not prove. And then Cauchy, the great French mathematician, ended up proving that and developing complex number theory quite a lot more. Okay, so now we can go back to having this a bit of geometrical framework now. We can go back to this fundamental theorem of algebra and the attempts by D'Alembert and Gauss to prove it. But they proved it in a more general version, the version that's more familiar to students these days. So the fundamental theorem of algebra is that every non-constant polynomial, say p of z, has a complex 0. That means there's a complex number z0 for which p of z0 equals 0. And combined with Descartes' understanding of the connection between the zeros of a polynomial and its factors, once you know that the polynomial has a 0, then you can create a linear factor from it, and you can then use that successfully to factor a polynomial into at least linear complex factors. those zeros are in complex conjugate pairs, and so you get quadratic factors. So from this, with a little bit of work, we get the earlier version that I've already stated. So this is the crucial kind of argument. And I'm going to talk about proof of D'Alembert, who was a very interesting French mathematician, 1717 to 1783, well connected in Paris, contributed to Diderot's encyclopedia, and had rather a strange upbringing. His mother abandoned him on a church when he was just an infant, and his father ended up rescuing him. His father was a prominent person, ended up rescuing and getting foster parents for him, and then funding his education and supporting him. But, so he came from rather unstable beginnings to do quite well. So D'Alembert's proof, so he gave a proof, well, which was not exactly complete. It was an argument which was then successfully honed by other people in decades to come. But I'm just going to sketch the proof here. So the proof rests on a lemma of his that has his name attached. And the lemma is that if P of Z is a non-constant polynomial function, and P of some particular value Z0 does not equal 0, then any neighborhood of Z0, by that we mean some little circular disk, contains a point, say Z1, such that P of Z1 in absolute value is less than P of Z0. So this is all happening in the complex plane, and I might draw some pictures here, take some getting used to thinking about these kinds of things if you're not used to it. So there's a copy of the complex plane, there's another copy of the complex plane, and we're thinking of the polynomial P as taking points in the one complex plane, giving us points in the other one. And we're assuming that we've got some point Z0 over here, and its image under P is some point over here, P of Z0, which is not the point 0. Okay? And the lemma says that no matter what little circle you draw around Z0, even if it's very, very small, you can find a Z1 somewhere in there, so that when you look at the image of Z1 under the map, you get something which is closer or smaller than P of Z0 in absolute value. So that P of Z1 will be closer to the origin than is P of Z0. Or to put it another way, it's not possible for that entire disk to get mapped to something like this, where all the points are bigger than or equal to, in absolute value, P of Z0. That's not possible. All right, so let's have a look at D'Alembert's proof now. So, of this lemma that we've just stated. So we're working in the complex plane, and we have some complex number Z, and we have some polynomial P, and let's write that out as A0 Z to the n plus A1 Z to the n minus 1 all the way down to constant term A sub n. And what we're interested in, what happens when we go to some nearby point, say point z plus w. So we're adding some small complex number w to z. So p of z plus w is a0 z plus w to the n plus a1 z plus w to the n minus 1 all the way down to the constant term. Now we can write this out in terms of its dependence on w. So all the things that don't involve w, a0 z to the n, a1 z to the n minus 1, all the way down to an. And then there will be something, I'll just write it capital A1 times w, and then something capital A2 times w squared, and so on all the way up to the highest power of w that will appear as w to the n, so I'll have an a sub n w to the n. So these a1s, a2 up to an, there's some expression involving the a's and the z. And what we do know is that not all of the terms a1 up to an are 0, since we're assuming p is non-constant. If they were all 0, that means that the polynomial doesn't depend on w. It means it would be a constant polynomial, but we're assuming we have a non-constant polynomial. Otherwise, we can't get a 0 of it. All right, so what we then do is we rewrite this as, this first term is just p of z0. And then we go down this list and find the first one that's non-zero. So it could be that this is non-zero, in case which we'll use this. But if that's 0, we might have to use a2, or may have to go down further in this list. So we'll suppose that the next one is a sub k w to the k. And then there's some other stuff which I'll write as epsilon, the rest. Okay, so this is the first non-zero term involving with AIs. And what is the epsilon? Well, the point is the epsilon is just all the rest of the stuff, and that's small if w is small. Well, in fact, that's very small if w is small, because the powers of w that we're looking at here are increasing. We're thinking of w as a small complex number, maybe like this. And so if you take a high power of it, you get a very, very small complex number. Okay, so this might be of degree k, and the next one will be degree k plus 1. And compared to this will be small if w is small. That's the idea. Okay, so then D'Alembert says, all right, let's just have a look at this. What happens to this as we move w around a little circle? Okay, if w goes around a little circle, what happens to w to the k? It also goes around a circle. In fact, it goes around a circle k times. wk goes also around. And when I'm saying a circle, I mean wk would probably be going around a circle like that. But I'm going down around k times for every once that w goes around, because of the way the angles add when we multiply complex numbers. So wk goes also around k times. And what that means is that this expression, here's our polynomial. Let's say the polynomial is mapping over here, and here is p of z0. So if we look what happens to z plus w as w goes around, in other words, we're looking at going around that little loop around z, then the image around here is going to go around here k times. So there's p of z0 plus a sub k w to the k. Well, because we ignore this epsilon term. And that proves his little lemma, because that means in particular there's at least one place where we're going in the direction towards the origin. There's one direction at least where we can go and the value of the polynomial is getting smaller in absolute value. So in this direction, it heads to the origin, so the absolute value decreases. So that's sort of a sketch of a proof of D'Alembert's lemma. Okay, and then he gave an argument to finish the proof, but in fact that wasn't really pinned down until quite some time later. So there's a theorem of Weierstrass in 1874, which is also pretty well known to undergraduates, that a continuous function on a closed bounded region assumes its maximum and minimum values. Let me illustrate that in the case of one variable function. So if you have a function on a closed bounded region, so in the line, that means a closed interval. That means an interval including its boundary points. That's what closed means. So if you have a continuous function on a closed interval, maybe it looks like this. So here's a function f of x, and x belongs to this interval a, b. And Weierstrass says something about the maximum and minimum values of this function. So here, you can see the minimum value is right there, and the maximum value is right there. And the function actually does take on that value. It doesn't just approach that value, it actually takes on the value in the interval. There actually is some interval, some point in the interval, say that one there, where the function takes on the minimum value, and there's some point in the interval, namely this one here, where it takes on the max. That's to be opposed to the following situation. If you had a function which was only defined on a half-open interval and looked like this, still a continuous function, but maybe it's approaching the value 10, but not actually getting there, because this point is not in the interval, because the interval is not closed. So this is the case where Weierstrass' theorem works. This is the case where it doesn't work, doesn't apply there. Okay, so this was a good time after, more than 100 years after D'Alembert, before the nature of continuity had been studied sufficiently so that people could be confident about arguments with continuous functions. In D'Alembert's day, in Gauss's day, continuous was just more pictorial rather than more concrete. Weierstrass and his colleagues made it a lot more concrete, and they were able to work with it more. But nevertheless, D'Alembert had this basic idea, and so his idea was the following. All right, let's suppose we have our polynomial, p of z, and we're looking for a zero. Try to prove that it has a zero. How do we find a zero? Well, you choose some radius r, which is big, and if the radius r is big, then the polynomial p of z behaves a lot like the leading term. So it behaves a lot like a0z to the n for mod z bigger than some r big. As when you look at very big values, the first term dominates and all the other ones are relatively inconsequential. Meaning that if you're outside this region here, then the image of the outside is going to be far away from what's happening inside here. So let's have a look at the image of this region in the plane. And suppose that the image was something like this. So in other words, suppose that the polynomial didn't have a 0, that it managed to not take the value 0. It managed to avoid taking this value 0. Well, then D'Alembert says, okay, well, this is a closed, bounded region. So if we think about defining the absolute value function, so we combine this with the absolute value of z, that will map us to just the ordinary real line. So we're going to go from here, this polynomial, and then we're going to take the absolute value. We're going to get some region. So just taking the absolute values of all these ones here. The absolute value is some point on the real line, some positive number. And there will be some minimum place. So that function will have a minimum value. There's the minimum value. And then Weierstrass's theorem and sort of the intuitive pictorial understanding of D'Alembert says that, okay, at this point here, this minimum value is actually taken on. There is actually some point over here, call it Z0, which gets sent to this minimum value. Okay, but that now contradicts his lemma, because we just discovered that if Z0, its image is there, then if we look around Z0, we're going to find some point which is closer to the origin than Z0. We can always find something that's closer to Z0. So we can never have such a situation where that's absolutely the minimum distance. So that contradicts the lemma. So we get a contradiction, and the reason for the contradiction is because we assumed that the polynomial didn't cover 0, that didn't take on the value 0. And so D'Alembert says, therefore P of z must equal 0 for some z in C. Okay, it's a very nice idea. It sort of is roughly convincing. It does depend on some arguments that people had to think about in the decades, in fact, the century to come. Try to make it tighter. Gauss then arrived on the scene and said, all right, I'm going to try to cook up a better proof. And Gauss realized that this was an important theorem. And he went back to this theorem many times during his career. He ended up proving it 3 or 4 times with different ideas. I guess he was perhaps never quite satisfied with his proofs because they maybe were not entirely watertight according to his high standards. So Gauss gave several proofs. And I'll just give you one of them. So his idea again is we've got this polynomial P of z, and if A is a complex number is z, then we say that the A is the real part of z and the B is the imaginary part of z. Okay, that's standard terminology. So Gauss says, all right, let's look at the x and y components of P of z. So he says, let's look at these curves. Look at the curves, real part of P of z equals 0, and imaginary part of P of Z equals 0. These are curves in the plane. So they're curves over here. Maybe one of them, the real part of P of Z equals 0. There might be quite a lot of them. And then there's some imaginary ones. Imaginary part of P of Z equals 0. Point is, if you have a polynomial, you can expand it out and you can rewrite in terms of A and B what the real and the imaginary parts are of that polynomial. Well, you can describe those curves. You can write down equations for those curves. Then Gauss said, all right, what happens when Z is large? For Z, a very large complex number, well, the curves are close to the curves, real part of, again, just like D'Alembert, the highest power of the polynomial, the first power, A0, Z to the n, that curve equals 0, and the imaginary part of A naught, Z naught, Z to the n equals 0. So in other words, when we're very, very big, the polynomial just looks like a pure power, and those functions are very easy to describe these curves. In this case, the curves are lines through the origin. Okay, so I'll give you the story in so here's X and here's Y. Then for example, small example when n equals 2, then we're looking at, these are the curves when the imaginary part of Z squared equals 0. And these other ones, maybe in blue, those are the curves where the real part of Z squared equals 0. And moreover, if you look at a big circle, and look outside a big circle, just as in here, you see that the blue and the white ones alternate. These on the boundary of a big circle, they alternate. So that's what happens when we look at it very far away. Well, what happens sort of closer? In reality, maybe I'll just go over here. So what Gauss has concluded is that if we look at these two kinds of curves, then outside a big circle, we get a picture that looks something like this. We have some white curve, and maybe another one there. And then well, maybe, yeah, this one will be blue. Maybe the white ones look like this. So far away, when you're looking at these curves, you see these pretty well straight lines. 4 white ones in the case n equals 2, the 4 blue ones in the case of n equals 2. And they alternate going around. And what is Gauss trying to do? Gauss is trying to argue that somewhere the white and the blue curves must meet. So it's a question of join the dots. You've got a white curve here. You've got these 4 lines coming into this circle, white, and 4 blue ones coming in. They're alternating. And you have to join up the whites to the whites and the blues to the blues. And Gauss says, obviously, these curves are going to cross somewhere. We don't know exactly what they're doing in here because the action of the polynomial can be rather complicated. But it doesn't really matter what they're doing. Somewhere there's got to be a place where these curves are meeting. For example, there or there. So Gauss argues somewhere the curves meet. And he said it in some way such as, you know, anyone would see it's quite reasonable that this should happen and so on. Okay, but in fact, you still have to make an argument, and Gauss probably realized that the argument was not quite watertight. You still have to give some reason for it, even though it was somehow geometrically obvious to him. But during this time, topology, which is concerned with continuous curves and, you know, how things are knotted up, had not really been developed. So Gauss was sort of pushing the boundaries of the thinking of the time in this proof. So even today, one should say, right, the fundamental theorem is a theorem that most undergraduates rarely meet. Pretty well the only place where you meet a proof of it is in a course in complex analysis. So in complex analysis, it's routinely proven, but that does involve a fair amount of machinery. It's a very simple to state theorem, and you can see that the 18th century people appreciated its importance and tried hard to wrestle with this fundamental theorem. And it's still, in some sense, a little bit of a problematic topic, as I discussed in my Math Foundations YouTube series. Okay, so next time we're going to talk a little bit about differential geometry and the origins of differential geometry. So I'll see you then.